Good evening, everyone, again. So, I think we have about 12 people. So, let's start. Uh, so, so, I'm Lakshit Singh. So, I'm an undergraduate of SLIIT, and I'm also a Microsoft student ambassador currently in the beta. I worked as an IoT Internet at Microsoft in 2021, and currently I'm working as a DevOps engineer at the same place. You can reach me via this email address for any concerns. Yeah. So today's content is mostly focused on IoT and stuff related to IoT, such as the protocols and development and design methods. So first we will be looking into what is IoT, and then microcontrollers, sensors, actuators, the main components we are working with when we are working with IoT. And then we will be looking into MQTT, which is a protocol we are using mainly in this IoT and electronics field. Then we'll be looking into the connectivity, basically network connectivity. And then I'll be speaking about design and development of these IoT solutions. So I'm hoping you guys can interact with me here, like using the chat. I think, yeah, everyone has the access to that. And you can ask me questions and feel free to use the chat anytime for ask questions or uh, present your opinions. So yeah, here's a place to use the chat. So what do you guys think about IoT? Like, what is your opinion when the name IoT comes to your mind? You can use the chat and say what you think about IoT. I'm not asking about the meaning of the abbreviation. It's Internet of Things. I'm asking about what do you think when the term IoT or Internet of Things comes to your mind? Like, what's your personal meaning for that or personal definition for that? Sorry, I haven't been sharing my video. You can express your idea or definition using the chat. Like, yeah, I'd love to hear your ideas about like what do you think when you're joining this meeting, what you will be expecting to learn here. Yeah, one person has sent a chat. Let's see. Connecting devices together to control the central control in centralized system. Okay, yeah, somewhat correct. And yeah, we can add more into that. Yeah, without wasting more time, I'll continue. So actually, it's a set of objects, physical set of objects with sensors, processing ability, and software with other technologies that connect and exchange data with other devices and systems over the internet or other communication networks. So in here, the things stand for the objects which consist of sensors and actuators and sometimes other technologies such as uh, minimal processing, we can call it edge computing, and those things are connected to each other over a network. So this internet, in the term IoT, the term internet is not standing for the internet we are talking about in our daily routines, like the internet we are communicating right now. This internet, in sense, the network we are using to communicate uh, between these the things in the sense these devices which we are used with sensors and actuators. So in here, this network could be the internet, like any other. It could be any other wide area network or a personal area network or a local area network or anything. So mostly it's a TCP/IP based network, but most of the time it becomes the internet. But in industrial environments such as factories and agricultural fields like stuff, in there this network is a local area network most of the time, and there will be the servers and stuff which are dedicated for this IoT service will be fixed inside this network. So the devices can talk to each other within that network without entering to the internet. So in the simplest word, a network of embedded systems which communicates with each other, devices and systems. So let's see what is an embedded system. So according to the definition, embedded system is a combination of computer hardware and software designed for a specific function. So this specific function could be washing clothes, such as the washing machine, and maintaining the in climate, such as a air conditioner. We can also nominate the electronic doorbells we have nowadays as a embedded system. So this embedded system has an electronic circuit, like an electronic system, which works for a specific purpose. Like it can't be used for general purpose. Like we can't use that system to calculate any numbers or anything, or we can't use that system to take photographs. We can't use that system to send emails or anything. That is only made or designed specifically for that function. So such a system we call as an embedded system. So in an embedded system, there are sensors, then actuators. So in the left side corner, you can see sensors, and the right side corner there are actuators, and in middle of that there's a processor. So and sometimes these sensors and actuators are not digital, so those are analog. So in that cases, we need to convert the signal sent from these sensors to digital signal. So then only the processor can understand. So in that cases, we have to use analog to digital converter. Similarly, in the case where the actuator is also analog, we have to convert this digital signal sent from the processor to an analog signal. Then only the actuator can understand it. So we have to use a digital to analog converter. So these are not compulsory things, but it depends on the nature of these sensors and actuators we use in the case. And also, it's more like a general purpose computer. There are memory also there, and memory and some other components we usually have in our computers also. So when such an embedded system is accessible by a network, we can call it as a Internet of Things device. So because the device, so just the embedded system device is just a device, but when we are connected to the network, it becomes a network of things. So we call that as Internet of Things. So now you have some idea about what is IoT, but I would like to also so with that idea, you think so you can use this IoT for different areas. So like you can say what are the applications of IoT? Like you can use the chat to uh, tell me what are the applications you think that IoT can be used in. So in the right side of the slide, I have mentioned some, but those are not the applications. Those are like the industries and fields where IoT can be used. But in those fields, there are specific use cases. Like as an example, uh, if I say, uh, yeah, doorbell, uh, electronic doorbell, so we can make it a smart electronic doorbell where like the in like in general purpose electronic doorbells, there's like we can press the button and then there's a device inside the house. So from the inside, like from the device inside the house, the people inside the house can talk to the people at the door. So like this. But when we get that to the IoT level, so that then the doorbell will be connected to the smartphone via internet. So then the people can talk to the person at the door over the smartphone, like from anywhere in the world, like that. So you can add any applications you think of where IoT can be used. Use the chat, please. So meanwhile, I'll express some of the areas IoT is used. So yeah, smart homes, the example I mentioned earlier, and smart cities. So in smart cities, IoT is heavily used. So even in the parking, when we are taking parking tickets, and yeah, mostly in parking tickets, the parking ticket systems are interconnected using internet, and this using this ticketing system, you can just uh, reserve a parking place, as well as you can pay for the parking place according to time, as well as there are like many uses of that. Okay, agriculture, yes, agriculture is using IoT. Yeah, agriculture, then healthcare. In healthcare, we can use this, even the fitness trackers we are using nowadays and smartwatches. Those are tracking your health. Like they can track what are the, uh, how many, what is the oxygen level of your blood and how many steps you have taken, likewise. So that is also synced with your phone and the data will be sent to the cloud. So in that case, it is also can be considered as a IoT device. And in transport, like even nowadays, like the smart cars like Teslas, they have many IoT features built inside them. And security, like we can also take the modern day IP CCTV cameras where the CCTV footage can be viewed over the internet. And there are pet care solutions like the bells we put on our pets, like cats and dogs, so where we can track them over the internet. Yeah. And in IoT, there are three layers. Like if we take the IoT into architecture, there is a 3D architecture where there are three layers, and in the top, very top, there's the application layer, in the middle network layer, and the very bottom, the perception layer. So this perception layer is the physical layer, but we will be mostly interacting with. So in the sense the outside world. So the physical layer consists of sensors, actuators, and some minor processing bodies, like more like a microcontroller. So it can sense the environment, or it can emit something to the environment. And so this microcontroller within that device can select what are the like it can process the inputs at up to a certain level. Let's take an example. So if there's a doorbell, so when someone presses doorbell, there should be an action, like there should be something triggered to send an event to the whatever the customer sent. So in that case, there need to be some processing. So in that case, there's some edge processing there. We call it that processing happens at the perception layer as edge processing. So it can reduce the network usage, network congestion. Like otherwise, the sensor has to communicate with the servers in the very top application layer. But this edge computing or edge processing thing reduces that network usage and make it more efficient and make it more fast to get the response of to communicate that data. And in the network layer, it is basically responsible for communicating via this network from like perception layer to application layer. And it binds these devices, like devices in the sense what are these uh, devices with IoT sensors or actuators. Sometimes the device can contain a sensor or an actuator, and sometimes the device may be contain both sensor and the actuator. And in the application layer, it is what responsible for processing this data. And it like all the data collected from like thousands of, maybe like 1 to 100 or maybe thousands of IoT devices will be collected at this application layer. And then this application layer process that data using different methods. We can use machine learning or whatever these modern techniques to do the processing. And also the most important thing, the human interaction will be happening at this application layer. So let's assume there's a IP CCTV camera where you can watch the footage via internet. So in that case, you watch the footage at this application layer while the footage is captured at perception layer. So the human interaction happens at perception layer. Like they can manage, like they can turn on and off these IoT devices, or they can like change the nature of the IoT devices. Like if they want, if there's a let's assume there's a IoT water, yeah, IoT doorbell or something. So in there they can like if we integrated all up to that, we can using the application layer, uh, the user can turn on or off, like lock or unlock the door using the application layer. Likewise, so the application layer is used for human interactions as well as the data processing. So yeah, I earlier mentioned, like when I'm explaining the embedded systems, I mentioned about the microcontrollers. So I'll explain it a bit. So you might have heard of microcontrollers like from like 5, maybe you are like 10 years, yeah, 10 years old, but this microcontrollers thing might be new to you. So let me explain the difference between this. So this microprocessor is just the processing part, but when it comes to microcontrollers, it consists of various parts other than this processor. So the microcontroller contains one or more CPUs. CPU is the microprocessor, along with memory, programmable input-output peripherals. So input-output peripherals in the sense, in here, like most of the IoT, when we come to the IoT stuff, we use this pluggable modules, such mostly sensors and actuators. So those are considered as input-output peripherals. So these peripherals should be pluggable, like we should be able to connect them. So there should be interface for that. So this microcontrollers comes with those interfaces to connect other pluggable devices. And so in most of the things, you might see these pins around this. So this rather than just a microprocessor, in the microprocessor there's only these registers and this ALU and control unit. But in a microcontroller, there is a AC/DC converters, IO peripheral operators, then RAM and everything inside. And so, and microcontrollers are optimized for dedicated work, like we earlier mentioned in the embedded systems. But microprocessors are used for general purpose work, mostly what we are using in our computers. So this is more like confusion, development boards versus microcontrollers. So you have heard of like Arduino, Raspberry Pi, maybe Node MCUs, ESP32s, likewise. But actually, most people think these development boards are equal to microcontrollers, but actually it's not. So these development boards consist microcontrollers, but just microcontroller is just a part of the development board. The development board consists of like many parts other than microcontroller, but microcontroller is the main part there. So it's just an IC, one of the ICs in the development board, but there are other ICs to regulate the power, manage the input output, then manage the communication, other like communication in the sense wireless communication or whatever other like the device. So these development boards are mostly used for POCs in the proof of concept level. So we are like just think you are developing something and you want to check whether this works or not. So in that case, you do a proof of concept. So in proof of concept, what we are using is this microcontroller board, the development boards. So in that development board, like if you are planning to use a specific microcontroller, you buy the development board which is built with that microcontroller. Then you can use that development board to develop your solution in the proof of concept level. uh, and then once you can complete, like when you get the proof that you can do that, then only you create the specific printed circuit board for that. So that printed circuit board will be like have to plan that to accommodate all the required components. Like in the development board, there might be components that we don't really need, like just I think we are building a some IoT device which only accepts the digital sensors, digital modules. So in that case, the usual development boards have a analog input array also. But so analog input array also comes with an analog to digital converter and digital to analog converter. But if we are using only the digital sensors or digital actuators, we don't really need that part. So in that case, we can ditch that part and we can just create a printed circuit board with only the components we need, and we can put this microcontroller inside, and we can like build the solution more like more small in size, more optimized, and more power efficient. So that's when what we do in production environments. Production environments is like when we go to commercial production stage, we ditch these development boards and we only go with the microcontroller put into our own built PCB or printed circuit board. So when it comes to microcontrollers are made by various companies. So most popular ones are Atmel, Microchip, and XP and Texas Instruments. But you might have not be heard about these companies because you only might be familiar with the names like Arduino or Raspberry Pi. But actually, the Arduino is using these Atmel chips. So in Atmel there are multiple uh, brands of chips like ABR, Atmega, likewise. So these the chip you are using is actually from these companies, but the development board is what is more popular among you. So if you are using Arduino board, you might heard of the name Arduino, but you have never heard of the name the Atmel, which is the which is the company which created the brain of that development board. So the development boards will be discussed more later in these slides. Yeah, so let's discuss about the sensors. So sensors are the product which creates a signal out of the environment changes. So first of that, let's discuss what we can sense. So as humans, we have 5 senses. Yeah, we say we have 5 senses, but all these 5 senses cannot be captured by these sensors we have nowadays. But there are some sensors which can go beyond and capture what we can't even capture from our natural sensors we humans have. So basically we can see light, we can hear audio, and we can sense the heat and sometimes proximity and orientation also, but and sometimes chemicals too. But there are some stuff we can like we can't sense. So but when we are using sensors, there are some sensors which are made specifically to sense a particular set of sensors, particular set of yeah sensors. So we use camera, color sensors, LDRs to capture light, like capture changes or anything related to light, and microphones to audio, temperature sensors for heat, ultrasonic sensors, LiDAR to measure distances and proximity, gyroscope compass to measure the orientation or the direction, bearing or anything, and gas sensors for chemicals. And there are like many sensors available, more than this. Like as an example, we have PIR sensors and even buttons and keyboards. So I have some sensors. Let me show you. So, so here is a keyboard. Like we can connect to a Arduino board or what like even we can connect this to a Raspberry Pi, and I have plenty of these sensors. Yeah, this is ultrasonic sense. Like there are various types of ultrasonic sensors. Like this is I think HCSR4. Like it has 4 pins, but there's another ultrasonic sensor called HCSR5. So it can yeah HCSR5. It can calculate the distance more accurately than this. Uh, yeah. So I'll go to the next slide. So yeah, here I have added some photos of different sensors. There are thermistors which are used to measure the temperature, and infrared sensors. So infrared sensors can be used in different cases, like even in our whatever the like TVs, ACs, and everywhere we have infrared sensors, but there are some like that's the transitive infrared sensor, but in like to measure the distances and measure the proximity, we use this reflective types IR sensor. Then we have ultrasonic sensor, which I showed earlier, and gyroscopes, and like different sensors. So I go to the next slide. So there are two types of sensors, as I mentioned earlier, like analog sensors and digital sensors. So these analog sensors doesn't really have a proper uh, computing mechanism inside. Like it only can it has like some analog signal, like it can only send analog signal to the edge device. So the edge device should take that signal and process it and make it digital, then only it can process it. So in that cases, that edge computing part, whatever the microcontroller, whatever thing, need to have an analog to digital converter. But there are digital sensors which just directly output the digital signal. So in that cases, the microcontroller doesn't really need to have a digital analog to digital converter in that cases. So in analog sensors, the signal will be like this. It's more like a wave. So this wave will be sampled, like divided into smaller time frames, and check whether this time, and according to a predefined rate. Like sometimes it could be 256, sometimes it could be 512, maybe 128, maybe 64, whatever. So they divide the height of the wave, like the amplitude of the wave, and give a number. So if thinks this is the highest value, so they give it 256, and the middle value 128 likewise. So according to the height of the wave, they give a value. So like they divide it into the small time frames, and for each of the time frame they give the value to its height. So likewise, that's how they give a value in analog sensors, and that value will be considered a high value or low value according to a moderate value. Let's we can assume 128 as the moderate value if the 256 is the predefined rate. So in that case, if the value is more than 128, it will be considered as true, and if the value is less than 128, it will be considered as false. So it's similar. So in this case, it's only true or false, because if the voltage is similar or close to 5 volts, it will be considered as high and or true. Or if the voltage is similar or equal to 0 volts, it will be considered as false. So that's how the value is gained from these analog and digital sensors. So there's we can actually divide the sensors into another according to another feature as active and passive. So active sensors actually uh, send some energy, like emit some energy to capture the value, capture the response, and in passive sensors, it use the available energy outside to capture the value. So as an example, when we are using a camera, we don't really like, most of the time we can just take the picture without sending light sources. Actually, what camera does is capturing the light and creates the image, but we don't, most of the time we don't send the light. So in that case, it's a passive sensor. So, but in infrared, like if you take a LiDAR or ultrasonic sensor, it sends a pulse of light or sound and wait for it to come back and then measure the distance. So in that case, it sends a pulse. So because of that, it considered as active sensor. And yeah, actuators. So actuators, as I mentioned earlier, there are different types of actuators, maybe digital and analog. So here are some of them. We have most of the actuators are mechanical, like it moves with the signal, but there are some actuators like displays, bulbs, which are not mechanical, so which doesn't really make a move, but make some changes in the environment. Like here in display something, but doesn't really move anything. LED bulb just light up but doesn't really move likewise. So this is the most important thing when we come to net communication in IoT. So MQTT. So MQTT is the protocol. It's a protocol. So message queue and telemetry transport. So it's a light-based publish subscribe machine-to-machine network protocol for message queue size. So I'll explain. So this publish subscribe model is explained later in this session. And this message queuing thing is like when there are many messages coming, the processing part, whatever, like server, whatever, can't process everything at the same time. So what it does is it uh, queuing the, like according to the order the messages received, it the server queues these messages. So using that queue, the messages which came in the order will be processed. So this MQTT is such a protocol where all of these IoT devices use this, like most of these IoT devices use this MQTT protocol to communicate with their other end. So it is designed for remote, like devices which are used with battery power and in remote locations. So that's why, and most significantly, these are made for like low processing power devices, like small Arduino boards and other ESP32s likewise. So they only can provide the low power processing. So that's why this lightweight protocol is needed for this communication, and that's why MQTT is more important for IoT communication. And yeah, most importantly, to use MQTT, we need the TCP/IP network, where the MQTT protocol is at the top levels, top three layers of OSI/ISO model, and so and it can only be run on TCP/IP networks. Yeah, so let me explain what MQTT is. So it's a publisher subscriber model. So in this publisher subscriber model, what it does is it like if you consider something like uh, normal communication model, the when we send a message, the message will be sent to the uh, end of the like the receiver, and if the receiver is not present there, the message will be lost. So but in this publisher subscribe model, what it does is the message will not be sent to the receiver, but it will be sent to somewhere in the middle, and the receiver is also looking at that middle place. And if a message comes to that middle place, the receiver can look in, like listen to that place and get the message. So that's this publisher subscriber model. So the person who was sending the message, or the device which is sending the message, is known as publisher, and the device which is receiving the message or intend to receive the message is known as subscriber. So when to get the message which should come to the specific subscriber, the subscriber should be subscribed to that specific middle place. We call it as MQTT broker. So this MQTT broker can divide this publishers and subscribers into two different places, like two different dimensions, two different groups. So the two different groups will know each other. So if it it is done under three dimensions: space decoupling, time decoupling, and synchronization decoupling. So this space decoupling is that the publisher doesn't really know who will gonna get this data. So actually, it's like anyone can publish to this specific place. Actually, we can limit who can publish, but if we limit it to a certain set of people, so any of them can publish to that specific uh, broker, and there's a specific set of subscribers also, so they can get the data. So the publisher will not know which of these people will receive this data, but like maybe all of the intended subscribers may get the data, but maybe none of them will get. But because of that, the space is decoupled. So the publisher doesn't really need to know who will get this data, and subscriber is also doesn't really need to directly have a contact with this publisher. And time decoupling in the sense what, like the both of these publisher and subscriber doesn't need to be online at the same time. Like when it's like WhatsApp, so like when we send a WhatsApp message, the intended receiver doesn't really need to be online. Like so the message will be at WhatsApp servers, and then it will be go to the receiver once he come back online. So it's something like that, but more and more basic thing here. So the publisher and subscriber do not really need to be online at the same time. And see, synchronization decoupling says when a message is received, the in the receiving end, it is not it doesn't interrupt the work at receiving end. Like it that's why we are using a queuing technique here. As I mentioned earlier, the message will be queued until the receiver process it. So even though 100 messages are in the queue, the process will be like the receiver will be listening to the queue, and if there's a message in the queue, it will grab the message and process it. If there's nothing, it will just continue its work. Yeah, so MQTT broker. So MQTT broker is that middle place where the messages are published and subscribers are subscribed into. So this is the heart of the MQTT protocol. So in here, actually this can there are two types of MQTT brokers which are managed and self-hosted. So managed are the ones which are available in the cloud platforms such as Azure and AWS. So in Azure we have IoT Hub, and in AWS we have IoT Core. And yeah, and there are some self-hosted like free open source MQTT browsers also, so we can download them and install it on our own machines. So those are MQTT and HiveMQ. So there's a free and available MQTT broker available in Mosquito. As I remember, the URL is mqtt.mosquito.org. So where you can use it as a public MQTT broker. Yeah, so in MQTT, the messages are sent to a specific topic. So people just think, so this temperature sensor is publishing to the topic temperature. And if there's any device also subscribe to that topic temperature, that device will only get the message. So in here, this laptop has subscribed to the topic temperature. So when at any time this temperature sensors publish something, this laptop get that message. And this if this smartphone published to the topic, it's lamp, right? Yeah, lamp. The lamp is subscribed to that topic, so it will get the message likewise. So we can have these topics are hierarchical. Like in here we can have a topic as home, and even within that topic can have first floor, second floor likewise, and even within that we have bedroom and bedroom two likewise. These topics are hierarchical, so according to the need we can use them in the manner. So like you can either create like home 1, home 2, home 3, or within home 1 you can create one floor 1, floor 2, floor 3 likewise. So yeah, IoT connectivity. So connectivity is the one of the most important things in IoT. Like otherwise, it will be just an embedded system. So this connectivity is the connected type changes according to the nature of the IoT solution. So they are could be like delay sensitive IoT solutions, and there could be IoT solutions which are specifically placed somewhere, or which are uh, in mobile, like self-driving cars or fitness trackers. And there are also set of network connected type, which is the two ends of the connectivity connection. So it could be either two IoT devices, or it could be a IoT device and another and a PC or a smartphone or something. So this thing to thing, which is known for this IoT device to IoT device connections, which are mostly used in ad hoc networks. So just imagine like we are implementing some IoT devices in a forest. So the forest, when it goes inside to the forest, the signal is there are no any mobile signal or anything. So the sensors, the IoT devices in the middle of the forest will not be able to communicate to the servers. But if we build up an ad hoc network, like a network where IoT devices communicate with each other and send the data from one to another. In that cases, we can use such a solution to this forest application, and we can get the data from the IoT devices which are built inside the forest and to the servers in the outside the forest. So likewise, there are different kind of networking types. And so yeah, here I have displayed the connectivity options available for IoT. So it depends on the distance between the IoT devices like IoT device and the connectivity place and speed and power. So if the distance is very low and it has low speed or power, we can use some technologies such as Bluetooth and NFC. But if the distance is still lower but it has some higher power or high speed, it requires higher speed, we can use Wi-Fi. And if the power is really low, like just think about some IoT equipment which runs on batteries and it will not be recharged frequently. In that cases, we have to use a very low power communication method, and in that cases, we can use NB-IoT. So NB-IoT is a extension of the 4G networks we are using. Actually, it's not uh, established parallel to 4G, but it's something developed from 4G. So in this case, NB-IoT instance narrowband Internet of Things. So this can be used for the IoT devices with very low power consumption and for which are in a very large distance from the tower. So I think NB-IoT can communicate up to 36 kilometers. Yeah. Similarly, we can have like if we have more power and if there are small distance, we can use 4G, LTE, 3G or 2G, and even satellite. So satellite communication is the most expensive thing. So it can like we can use it for longer distances, but it consumes more and more power as well as more and more money. So when you're developing these IoT solutions, there are some standards and frameworks. So these are mainly for to maintain the interoperability. Like if there are multiple people are creating these, developing these IoT solutions, these solutions should be able to communicate with each other. In such cases, we need these standards and frameworks. So this defines methods for data sharing, interoperability, and security for these networks, IoT networks, and this is considered seriously when it comes to commercial development of IoT solutions. Like if we are developing something for our own use, it's not really a concern. But if you are developing something for commercial purposes, we really have to consider about these standards and frameworks. Yeah, design and development tools for IoT. So as I mentioned earlier in this session, like there are development boards. So these development boards consist of microcontrollers, power circuit, programming interfaces, basic input, output, and yeah. So this programming interfaces in the sense the connectivity type we are using to connect these development boards to our computers. So there are I2C, SPI, UART, likewise. So each of these development boards have different like interfaces. Maybe some have all three, but some have only have one. And power circuits also same. So some works with 12 volts, some works with 5 volts, likewise. Microcontroller is always different. Like in Raspberry Pi boards, it's a different microcontroller, and in Node MCUs, it is a different microcontroller. So these development boards are mainly used at development stage. And like as I mentioned earlier, we use this to for proof of concepts. And this when we go to production stage, we dish these development boards, and we create a printed circuit board with only the components we need. Yeah, so there are some criteria when you are selecting a development board. So mostly what we can consider is this processing power and memory. So if we need like if we doing image processing or something, we really need to go to something like Raspberry Pi, which has a higher processing power and higher memory. And we also have to consider about the form factor. So if we are developing something very small, like a fitness tracker, uh, or a smartwatch, the form factor have to be really small, and whether it should be like we have to consider whether it should need wireless capabilities like Wi-Fi, Bluetooth, or anything, and scalability of the input output. Just think like this Raspberry Pi board has 40 pins, I think, but if you don't really need 40 pins in the future, you can just go with something small. It doesn't really have 40 pins. Like there are smaller variations of these Raspberry Pi boards like Raspberry Pi Pico, Raspberry Pi, yeah, likewise. And cost is also a concern. Like if you are developing this for like large scale for mass production, we have to really look into the cost also. And compatibility is also a concern. Like if you are using a, a, a framework like Arduino, we can use Arduino boards or Node MCU boards or ESP32 boards, but it will not run on this Raspberry Pis. So we have to consider the compatibility also. And community and support is also much something important. And because if you are an individual who is developing this, the community and support is really important, because if you have any doubts or if you have any questions, you can fix them using by referring these community blogs and uh, wikis. Yeah, so these are the IDEs and software tools we are using for development of IoT devices. So we use as Arduino as an IDE, so it's the most popular one. So we are using that for Atmel and ESP-based microcontrollers. Uh, then we go to the Node-RED. So Node-RED is a flow-based development tool. So IoT solutions, we can use it for other solutions also, but we use it as a main tool for IoT. And we have Walkfree and Tinkercad for this simulation purposes. We can like use Arduino within this Tinkercad platform to simulate the Arduino code with some actuators and sensors. And for ESP related microcontrollers, we can use Walkfree. Yeah, and IoT services. So IoT services on cloud. So in this cloud platforms such as AWS, Cisco, Azure, IBM, Watson, and Google Cloud, they provide different IoT services. So like there are mostly those are MQTT brokers or something similar. So that's why most of them are available on MQTT and HTTP protocols. But if we consider something like I think yeah, there are some platforms like Azure which have their uh, own communication protocols for communication between these IoT devices. Mm, yeah, so I have some sample codes here. I think let me show. Yeah, that's like I have developed some IoT projects during the last couple of years, like a digital thermometer uh, and a air quality measuring system, and likewise. Let me show you. Yeah, so I think you guys can see my screen. Yeah, so this is a Raspberry Pi based digital thermometer. Actually, what it does is it reads the temperature from this DHT11 sensor, and it shows it using a meter used with the servo motor. So the code is actually, in this case, the code is actually really simple. So only have 45 lines. So first you have to define what are the as a libraries you are using and what are the pins you are using. Pins in the sense the input pins available in the Raspberry Pi board. Then you can just define how these sensors will be used, and like we can define in which pin this specific servo motor is connected, likewise in which pin the sensor is connected, and then you can write the code. And like it's just 45 lines, like it can fit in the screen like easily. So the code, like the code is differ from this platform to platform. But when we are writing in Python, we have libraries for Python, we have libraries for C++ platforms such as Arduino. So according to the platform we are using, we have to consider, like if we are taking a sensor, we have to check whether the sensor has a library for that specific platform, and then only we can use it on platform. So that's mostly about my session today.